So, welcome to the 7th Geopolymer Camp. I'm every year presenting what I call the state of geopolymer research and development. That is to say, I present what I consider to be important in terms of recent news that happens this year or last year, so that if you look at the previous video that we have put on our internet site at Geopolymer Camp, we started in 2009, 2010, 2011, 2012, 2013 and 2014, and it is a great source of information regarding the developments that are going on in the world of geopolymers. So you'll find really breakthroughs that are presented there, together with the keynotes that are every year presented during the Geopolymer Camp. So there are several videos that are very worth to watch on the internet. The numbers of registered participation this year is higher than previous years, which for us represent some problems in the organization. But as you see, majority is coming from Europe. This is easier. But we have still more representative from the US and from India, and the farthest are from Australia. This is a PhD student, and Chile and Brazil. The state of geopolymer, 2015 and not 2014, is split into 4 parts: geopolymer science, geopolymer technologies, geopolymer cement and concretes, and geopolymer and archaeology. Today I will not talk about geopolymer and archaeology. We don't have any recent news on it. We can discuss it later. I start with geopolymer science. This is how it started. We come back to our first conference in 1988 on geopolymer. There were 1, 2, 3 laboratories working with us on the development of products, and this is what we have presently or more. And so you see that this great increase in institutions working on the subject will have an influence on the amount of published papers, essentially scientific, patents, and so forth. We take the reference, this is 1991. 1991 is my first official scientific paper published in a so-called peer-reviewed journal. And it is the most cited papers in geopolymer literature. And we had 1 or 2 publications per year. And you see, during more than 10 or 20 years, practically nothing happened. And then it started to increase, and now this is an exponential trend. We are, in 2014, we had more than 470 papers. And this raises some questions. Why do we have this sharp, exponential increase? From one side we see, well, wonderful, but from the other side I witness that it is quantity and not quality. And the majority of the papers are really low quality materials. And I started to look at what we could do, and I presented last year at the Geopolymer Camp, we should maybe try to find and to introduce a new journal of geopolymer science in order to select the best papers. And this is what I wrote. The Journal of Geopolymer Science should serve as a focal point of scientists, engineers, academicians, graduates and undergraduate students. The journal will be led by the founder of Geopolymer Science, assisted by world's reputed editors. It will be aimed at providing a dedicated editorial board, zero tolerance for plagiarism, and high respect for publication ethics. This is no longer the case in practically the majority of the publication. What we read in the published papers, scientific papers, is for us rubbish, garbage, is nothing. And except some that are very important, and the target is to select them. The peer review system that is normally there in order to select or to edit what has been written is no longer working. And those who are, like myself, accustomed to ask for peer review and so forth are really, no, I no longer want to peer review any papers because I am always disappointed. So we started to look at the system, and I wrote to the major scientific papers editors like Springer and Elsevier, and I received from Elsevier the answer, yes, we can do something. And we are starting something that is totally new with Elsevier, that is a collaboration with Elsevier to present a virtual journal on geopolymer science. But not just another journal. This is something that is totally different. We are studying, it is a collection of already published research papers, but we select those that we want to pinpoint, focus on. That is, we will have themes that will be presented, and these themes will be hosted on the internet site of Elsevier, especially in the Materials Today page. We will have several themes per year, and it is online since June this year. It has been online since 29. So one is Elsevier Geopolymer Institute research focus on geopolymer science. This is the comment, general comment. So you go to materialstudy.com, click on polymers, you will come back to this, okay, and either to comment or features, and you will get comment what are geopolymers. So the Elsevier editor is presenting to the community what is a geopolymer and so forth, and clicking on features. This is the first review paper on environmental implications of geopolymers. This involved, and I have this afternoon special presentation of this virtual journal of geopolymer science. Another improvement in communication and teaching is our webinars. On the internet, we started in 2013, and in 2014 we had very strong attendance. These have been the registered participant to these webinars. We had more than 210 registered participants that we split into two groups. This is obvious because we are talking to the entire global and we have 2 time zones for the west, for the east, or for the west, and well, the response is there, and it is, in fact, the best way to understand the teaching. And here we have put other various videos on the internet, on the page home, and on the page webinars, and we have 10 videos split into segments. Each of one is dedicated to a special theme: application and commercialization, what is a geopolymer, the 6 basic rules. For those who attended the webinars, they know about these definitions. Geopolymer science and pyramid, this is archaeology. Principle of aluminosilicate science, heat and fire resistant polymer, fly ash based geopolymer, durability test, geopolymer cement, and geopolymer science and Roman cement. This is available freely on the internet. You can watch them. These videos last between 15 minutes and 20 minutes. And of course, there's my book. This is the 3rd edition, and for those who want to have the entire papers, the entire videos that are already published, they purchase what we call the bundle for newcomers with these key that provides an additional system. So, most important part, geopolymers are inorganic macromolecules. Geopolymers are not a gel of unknown structure. We are talking about macromolecules, chemical well-defined systems. We are using alkaline polymerization and acidic polymerization. Today, my statement will include what I call a clarifying statement on what is a geopolymer, and I will develop it later. Until 1999, until the 2nd Geopolymer Conference that was held at Saint-Quentin, here, in this room, geopolymers equals advanced knowledge in aluminosilicate chemistry. This is how I presented it. Since 2002, that is to the 3rd Geopolymer Conference in Melbourne, organized by the Melbourne University, everything that is not Portland cement is called a geopolymer. So you see the shift. And this shift is presenting a lot of, or inducing a lot of problems. Geopolymer is not equal to alkali activated materials. Since 2005, that is since our Congress Geopolymer 2005, that we had here in this room, and also at Curtin University in Perth, Australia, I'm fighting against those who use the concept of geopolymer as an interchangeable synonym for alkali activated material. It is really a fight. Well, what is going on? The geopolymer concept goes beyond concrete. It is still wider. But because for many people, alkali activated material is equal to geopolymer, they consider that because for them it is alkali activation, that I am plagiarizing what the invention of Glukowski. And this is totally wrong. And thus, they published paper like this one, in which they replace the wording alkali activation with the one of geopolymer. And this is what they write. This is a paper, Life Cycle Analysis of Geopolymer, by a German team. According to the publications of Glukowski, geopolymers or inorganic polymer binder system had already emerged in the late 1960s, Glukowski. In Russia and the eastern part of Europe, some industrial application of geopolymers, railway sleepers, were reported. But it seemed that geopolymers were never in a state of mass production until today, until only niche applications, that is fire-resistant glue, exhaust fume pipes, heat and fire barriers, have been established in Western Europe. So, what this is a typical example. Glukowski worked on alkali activation. He did not invent the geopolymer chemistry and terminology. In this paper, everything that has been implemented and commercialized in Western Europe and USA is considered as being negligible. Only alkali activation is something valuable. Geopolymers are nothing, even if they are claiming and writing that they are doing geopolymer technology. This is a typical example of what I call historical revisionism. It is not the first time that I am witnessing this behavior. The problem is that if this would have been published in a very remote paper, publication, not accessible to anybody, it would not be important. But it has been published in a book that a lot of people have purchased, that is called Geopolymers, Structure, Processing, Properties and Industrial Applications, edited by well-known people, Professor John Provis and Professor van de Venter. Provis and van de Venter are from Melbourne, and now he's professor at Sheffield, in the book published in 2009. So this is a problem. You have books that are just a compilation of articles written by people who do not communicate between each other, and you have editors who don't care about what is written in their articles, in their book, or they agree with it. That is, they agree with the statement that the inventor of geopolymer is Glukowski. They could have asked the authors to write something different. I am not against Glukowski, I consider him as a good scientist, but I don't like when people don't respect what I have done since geopolymers have been invented 40 years ago. And I will continue my qualifying statement by explaining how it was invented. So, every alkali activated waste is called geopolymer. We have to stop this way of reasoning. But it is not the end. I continue. This is a report that has been written in 2014 by a well-known committee dealing with cementitious material that is called the RELAM, and on alkali activated materials, written by the same people as I talked previously. And we notice the following. In the context of this report, the terms alkali activated material, AAM, and geopolymer are at least worthy of some comments. Alkali activated materials is the broadest classification, encompassing essentially any binder system derived by the reaction of an alkali metal source. Geopolymers are in many instances viewed as a subset of alkali activated materials, where the binding phase is almost exclusively aluminosilicate, and highly coordinated. This distinction between this classification is shown schematically in figure 1 and 2. This is obviously a highly simplified view of the chemistry of concrete forming systems. Geopolymers are shown here as a subset of alkali-activated material with the highest Al and lowest calcium concentrations. So you have the domain of alkali-activated materials, the big ones, and you have the small domain of geopolymers. And these people are changing the wording alkali-activated and claiming it is geopolymers, and they say that the geopolymers have been invented by others at the time, and this has nothing to do with what we are doing. This is the situation. And this is the situation induced by cement scientists that are shifting to alkali activation and propagating this. This is disinformation. But this did not prevent the same people to write. It is also noted that the term geopolymer is also used by some workers, both academic and commercial, in a much broader sense than this. This is often done for marketing rather than scientific purpose. Geopolymer is something sexier than alkali-activated material, so we must shift from IAM to geopolymer when we go public. So on one side, for the scientists, the hard science, this is alkali-activated materials. When we go outside, this is geopolymers. So what is this? Nonsense. They make a lot of confusion. And the one who is writing this is Professor Prof. That doesn't prevent him for posting this job description. We are looking for a geopolymer scientist. They are propagating alkali-activated material as the real material, but when making an advertisement for job, they are writing geopolymer. So there is a big problem here. I am sure that if we would have written research associate in alkali-activated material durability, we would not have gone no candidate. For, according to Rilem, geopolymer is a type of concrete, nothing else, and this is wrong. So I have obliged to make publicly a clarifying statement and to show the history of geopolymer science and development and my connection with the alkali activation world. This is in 1975 that we discovered the property of metakaolin. In 1997, we invented our first mineral polymer resin. This resulted from the reaction between metakaolin and soluble silicate. So we used them to impregnate fabrics to manufacture items for the industry. And it is a resin, a binder that can be used for all type of products. 1980, more than 35 years ago. In 1979, I invented the geopolymer terminology because I wanted to have one thing that could be understood by everybody. For me, I was not a cement specialist. I didn't know about cement at all. For me, it was low-tech. I was not tackling cement at that time. And I presented the terminology based on the ratio SiAl, polysilate, SiAl2, polysilate siloxo, SiAl3, polysilate disiloxo, and if the SiAl is higher than 3, we have the silate link. Geopolymer is a polymer. And if you say geopolymer is a gel, it's marmalade, forget about the terminology and forget about the wording geopolymer and invent a new one. Geopolymers are polymers. They are processed like organic polymers, yet they are geopolymers, fire and heat resistant. This was our purpose at that time. My target was to invent a fire-resistant polymer, and we achieved it after 8-10 years of research and development. In 1979, we created the Geopolymer Institute as a non-profit scientific association. I put the word geopolymer in the public domain. The research on geopolymer was carried out in our own private research laboratories that we created in Saint-Quentin, family-owned research that was called Cordy Geopolymer, Cordy Coordination and Development of Innovation in Geopolymer Science. And this company worked until 2009, where we closed the lab. And since 2009, all the labs are within our industrial partners. What about the cement applications? They started in the US by Lone Star Industries. I've been invited by Lone Star Industry, not invited, hired to invent a new type of cement. Lone Star Industries was the major cement manufacturer in the Western Hemisphere at that time. So we invented in 1983 at the Central Laboratory in Houston the geopolymer cement that was called Pyramid. That is 11 years after I began my research on this new topic. It is there that I discovered, and then I had my first university appointment where I worked on archaeological science, applying this knowledge in order to understand what our ancient ancestors have also developed. The first pyramid patent was filed in 1984 and granted in 1985, titled Early High-Strength Mineral Polymers, by myself and the head of the Houston Laboratory of Lone Star Industry, Jim L. Sawyer. Early high-strength mineral polymer composition. It was the first time that we mixed our geopolymer binder, polysilate based, with a material that had absolutely no real value, slag, blast furnace slag, and we discovered, and this is the first invention, what I call geopolymer cement. The development was spectacular. This is something that I repeat each time, but there are a lot of people who are seeing it for the first time or the second time. Those who were here yesterday have seen it, but I repeat, that time the target was to make a very early, fast cement with high strength. And this is what we achieved. A crew begins placing concrete in Los Angeles. At the same time, a Boeing departs from New York. After 1 hour, the concrete is strong enough to walk on. After 4 hours, the concrete is strong to drive on. And after 6 hours, it is ready for the weight of a commercial jet. We started in 1983, March. I sold all my rights to Lone Star in 1989, and the pyramid was manufactured until 1997, when the company was purchased by acquisitions. You know, the companies, the private, they acquires and acquires and acquires, and it was no longer a material that was interesting for the company that acquired Lone Star and so forth, so it stopped. It works very well. This one was a very special Portland-based binder that is a mix of Portland and geopolymer material. But during this development, we had research and publication going on officially, and the US Army Corps of Engineers made the first study on what we were doing, and they tested what has been done in the laboratory of Pyramid Company in Houston, and they published an official report, Potential Application of Alkali Activated Aluminosilicate Binders in Military Applications. So I had, for the first time, the connection with alkali activation, since they were relying on what was previously studied by Glukovsky in Russia, at that time Soviet Union. And this was, became aware of Glukovsky 14 years after having started geopolymer science. I published my first paper on geopolymer concrete in American Concrete International from American Concrete Institute in 1987, titled Ancient and Modern Cement, What is the Real Difference? And geopolymer concrete may be a key to increase durability. Remember, this is 1987, 30 years ago. 1989, 2 years later, my friend Glukovsky published a paper at a symposium in Sweden, Durability of Concrete, Aspect and Admixture of Industrial Byproduct. This was the last paper by Glukovsky, titled Ancient, Modern and Future Concrete, based on my work. And then we had our first conference in Kiev in 1994 that was called Alkaline Cement and Concrete. At that time I was not against this appellation, since I thought maybe we could merge alkaline activation from Glukovsky to this new geopolymer science. And we were still at a time where the conflict was West and East, those from the Soviet Union and those from the Western Hemisphere. And I came to Kiev and presented our knowledge, which was totally different from the one of these people accustomed to a totally different background. And if you look at the proceedings of this conference, you see the major difference in wording, presentation, how the things are presented. We are presenting very clear methodological research and development. They are writing and writing and writing and writing and writing. But here we see the clear difference between alkali activation, that was their job, and geopolymerization, that was, at that time, my job. I wanted to meet with Glukovsky, but I had no luck. He passed away 6 months earlier, before the conference. But his paper was written, and this is what he wrote. These compounds are similar to those commonly found in the sediments and other thermal metamorphic rock-forming minerals in the earth crusts named geopolymers by the American scientist. At that time I was in the US working, so I was an American for them. So he continues to write, geopolymeric cement resembles the alkaline soil cement that they had invented. Yes, they resembles, but there are differences, and the differences are very important. The Kiev scientists learned from my teaching about the excellent durability and long-term property of geopolymer cement due to the reaction with metakaolin. They used Davidovits' work on geopolymer cement to improve the quality of the alkali activated material and coined it geocement. So they knew that the alkali activated material had a lot of flaws and drawbacks. It was not finished, and we will present it later on the video this afternoon on why are alkali activated materials not geopolymers. So if we come back to this representation of the RILEM committee published in 2014, where we have here geopolymers. Remember, geopolymer, as the wording, is a concept, it is not a product. And if these people want to, alkali activated material, want to follow Glukowski's teaching, they should write geopolymer cement or geopolymer concrete, but not just geopolymers. But I am asking them to erase it, period. I don't want to be connected with alkali activation at all. Geopolymers are made of different molecules. Here we are talking about aluminosilicates, and their properties differs from a function of the SIL ratios, because the SIL ratio will induce a different networking framework. We will have 3D network, very rigid, and we will have two-dimensional network, more flexible. And this is depending on the amount of SIL that are present. And of course, the applications are totally different. With SIL1, we do bricks, ceramics, and fire protection. These are the way of making bricks at low temperature. SIL2 to 1, this is the cement, because we include silicone coming from water glass and silicates, or radioactive and toxic waste encapsulation. Come back this afternoon on that topic. And when we increase the SIL ratio, then we enter into the industrial applications, those who requires different properties, ending up to fiber-resistant composites. These are geopolymers, and not just this one. This is the geopolymer cement or geopolymer concrete. It is not a geopolymer. A geopolymer is a concept. It must always be associated with a product. Geopolymer paint, geopolymer grout, geopolymer composite, and so forth. In 2008, we had a big congress in Verona, in Italy. It was the second International Congress on Ceramic. And I've been asked to present a roadmap on the development of geopolymer science. And I presented 14 research topics, each of which are different. I will come back. You'll find them on the internet, and I'm presenting it every year in order to show what are the progresses: phosphate-based, organic mineral geopolymer, long-term durability, geopolymer fiber composite, geopolymer ceramic processing, manufacture of geopolymer cement, geopolymer concrete, and material for medicinal application. There's a lot of research to be done in the world, and a lot of research to be done in the future. There's a huge potential for development. Point number one, most important one, this is the definition. What is a geopolymer? It is a polymer. And because it is a polymer, it will have particular microstructure. And the one for geopolymer is the fact that it is a nanoparticle. 10 micron. 10 nanos dimension, this is the small particle here that is the result of geopolymerization. It is not a gel, it is not something that is unknown, this is something that you see under the electron microscope. provided you do the real geopolymer. This is a study, 2003, it's now 12 years old. But it is knowledge that is unknown by the other party. They still are talking about gel and so forth. So we have the dimension of our geopolymer micelle. This is the result of geopolymerization that has the same dimension of a lot of organic polymers. Organic polymers are also coiled. This is something, the results of polymerization, either for plastics, nylon, polyethylene, epoxy, or for biopolymers, the DNA, and all they are all formed into coiled materials. This is something that is general, and we have the same for our geopolymer macromolecules. Geopolymer micelle, 10 nanometers. Colloidal silicate is quite big, for people it is small. Silica fume, real big, and this is fly ash that is bigger. Geopolymer is a nanomaterial, and it is not an unknown gel. Topic number 2, polysiloxanate, that is the chemistry, the knowledge on water glass. Water glass has been invented 150 years ago, but it is a chemistry that has to be reinvented and understood. And this is a study that has been done in France that provides some knowledge on the speciation of the silicon. We have silicon, Q1, 2 silicon oxide, 2 siloxo, 3 siloxo, and so forth. I don't explain it today. Those who are interested may go back to my State of Geopolymer 2014. If we continue, we have metakaolin synthetically manufactured. So we get the metakaolin from the carnatic clay, so it is a natural material, but for certain applications, for example, medicinal applications that requires 99.9% purity, and it is synthetically produced through 3 methods that are sol-gel based. This is also part of one of my State of Geopolymer, I guess 2012 or 2013. As for calcium-based geopolymer, I made a clear cut now this year about alkyl activation and geopolymerization, and I will be presenting I guess this afternoon in the next session the video why alkali activated material are not geopolymers. Rock-based geopolymers, is a new series based on iron that I call ferrosilate. Silica-based, these are the polysilanol, where there is no aluminum at all. And this is a system that is used in the industry to make resins for foundry cores. So you see, for those accustomed now in the geopolymeric structure, recognize the different elements. We don't have aluminum, we only have silicon oxide, siloxo, and silanol system. This is called sodium or potassium nanopolysilanol, because we have here fumes, silica fumes, that are linked with polysilanols. Fly ash-based geopolymer, I do not propagate the use of alkali-activated fly ash that is considered user hostile. This is also part of my different videos and papers. We have phosphate-based geopolymer, beautiful aluminum phosphate isomorphs. And then we have the organic mineral polymers, those that include the phenolic, latex, silicate, silane, epoxy, and the colleagues at Napoli Partenope University have discovered a compatibility rule between a geopolymer medium and an organic one. Normally they are incompatible, and this has been published in 2013. Novel hybrid organic geopolymer material, epoxy resin and metakaolin based polycide siloxo mixed. We obtain a good compatibility between the organic and the aqueous inorganic phase thanks to numerous hydroxyl tails, such as groups OH, that are formed during the epoxy ring opening reaction that make the organic phase temporarily hydrophilic, increasing the compatibility with the aqueous inorganic phase. It is not an interreaction between the two systems, it is the fact that they become compatible in terms of mixability. How it is working? So we have here the structure of our geopolymers. These are the various steps of polycondensation. You have the OH hydroxyl groups, and the epoxy group, during its own polymerization, this epoxy opens and builds an hydroxyl group, and this is the point, the time when they are mixable. Before that it is not, and after that it is too late. So this is published, you can get access to, and we have the keynote on that topic, a video keynote, I guess 2013, on Geopolymer Camp 2013. Manufacture of geopolymer cement. The problem that we were facing, we started 1985. We started from our knowledge, so we had 50% of potassium silicate in our system. And with the development of our knowledge, with the fact that we had to reduce the quantity of silicates in order to be cost efficient and to rely with, we'll see this afternoon, with the problem of environmental impact, we found a way to diminish the amount of potassium silicate that we are using. We started with 50%. The rock-based geopolymer cement only requires 20%, but we get 100 MPa. If we only put 70%, we get 50 MPa, that's high enough. And the fly ash-based geopolymer that we started in 2006, 100 MPa, 14%, and 10%, 40 MPa. So the use of the silicates are really very small. But people don't care. You'll see this afternoon, they start from the scratch and measure the CO2 exhaustion of a geopolymer cement, ignoring the fact that in the industry it is no longer what it was 20 years ago. But this is what the people are doing. Geopolymer concrete, we had our first airport built last year. This is the entire airport, I will come later on it, involving the ways, the runways and so forth, and the building. And number 15, I introduced radioactive and nuclear waste because we have now institutions that are working with geopolymer science. And the latest one, January 2015, from Japan, Waseda University, a new decontamination tool expected to help Fukushima clean up. I'll come back this afternoon on that topic. You see, we have the polysilate, and this is the structure here that is special and that is trapping the cations. So this was for geopolymer science. I continue with geopolymer technologies. I don't have a lot, I have some. I made a selection. I received a team from the industry who said, well, you know, in the industry there are two hot topics. The first hot topic is 3D printing, and the second one is geopolymers. I say, well, fine, okay. And then this year we have a publication dealing with making geopolymer components by 3D printing. Wow! This is what I'm presenting now. The abstract. Geopolymer components with high control porosity. The porosity is not important. This is where design and product by means of CAD, CAM and FDM fuse deposition modeling technique. PLA, this is polylactic acid, sacrificial structure with different patterns were 3D printed with high accuracy, and a geopolymeric slurry was used to produce closed inverse replica. And I present what they have done. You have the template, PLA, that they print, and then you have the geopolymer that results after having destroyed the template. This is 20 millimeter wide. How is it made? Method. They are using a fused deposition modeling 3D printer. You have seen these small 3D printers with a thread that comes through, it is fused and deposited. This is what they have done, but with a very special polymer. This is polylactic acid, PLA, filament, 3 mm diameter, was used to print the molds with a resolution of 0.1 millimeters. The external shape of the final lattice was a cube of 15 millimeter sides. You see, look, this is what we're talking about. Molds were designed to have open interconnected channels. PLA, this is a polylactic acid, sacrificial templates, which means the mold that will be then sacrificed, dissolved afterwards, impregnated with metakaolin-based fly ash geopolymer slurry. It was sealed, hardening at room temperature for 22 hours. After hardening, the sacrificial PLA template is removed. We directly immersed it in KOH, because it dissolved by KOH, at a temperature of 72 degrees C for 24 hours. So we have the nucleophilic attack of the organic polymer chain links with partial hydrolysis. Samples were then washed with hot water to extract the PLA. Subsequently, the samples were heat treated at 330 degrees C for 24 hours in a tube furnace under an egg flux. Complete PLA removal and retention of the geopolymer integrity. So one has to, and these are the geopolymer samples that were obtained. There are 4 different molds. This is 1 centimeter, half a centimeter. These are millimeters. Well, what can I say? Try. Okay? Second topic that I've chosen for geopolymer technology has been presented last year as a keynote by Zdeněk Kraua from the Czech Republic. This is the use of geopolymer binder for making core and molds in the Foundry. And what I'm presenting here is a very interesting video. This is why I'm putting it here. This is a Czech company. So now we come to geopolymer cement and concrete. There are a lot of applications. Several grout systems have been developed, but I love to show you the one that I prefer in terms of grout, and this is this one. But in fact, the major breakthrough came in geopolymer concrete, not from Melbourne, not from Perth, from Brisbane in Australia. Last year, 2 years ago, with the first structural buildings ever made with geopolymer concrete. The first, world first building to successfully use geopolymer concrete for structural purpose. We have 3 geopolymer concrete suspended floors, and this is how it looks like in real perspective. 1 floor, 2nd floor, and 3rd floor. This is a public building for public visiting, entering in it. This is how it is inside. We have the floor, and these are here the air conditioning systems. And it has been made with slag, fly ash based geopolymer concrete. This is precast panels by the company Wagner's. And the company Wagner's continued by developing and installing an airport. It is with their EFC, this is Earth Friendly Concrete Geopolymer. This is their brand name. This here is the concrete batch plant. And here you have the big machine that is making the turning nodes, the aprons, taxiways, the hangars, 43 half meter thick. I put the news October 14, 2014, 70,000 tons of geopolymer concrete for airport. In Australia on September 28, 2014, the newly complete Brisbane Camp Airport held a community open day, and this is officially announced, and this is one excerpt from the local newspaper. The greenest airport in the world, more than 30,000 cubic meters of world lowest carbon cement-free geopolymer concrete, Wagner's earth-friendly concrete, EFC. This is something that is really important, and the property of this material will be shown after the break in the video. Alkali activated materials are not geopolymers, because I am using this industrial experimentation to demonstrate the difference. The question: why did it take so long between the invention of the first geopolymer cement, 1983, and the real application in the field? 30 years.
In Australia. Only in Australia.
Well, it says only in Australia. Well, it started in Australia. But why did it take so long? I had my first answer in a review that I wrote in 2013 that is available as a technical paper in our Geopolymer Institute website. The existing Portland cement standards are not adapted to geopolymer cements. They must be created by an ad hoc committee, yet to do so requires also the presence of standard geopolymer cements. Presently, every expert is providing his own recipe based on local raw materials, waste, byproducts or extracted. There is a need for selecting the right geopolymer cement category, otherwise you cannot edit the right standards. My 2012 State of the Geopolymer RD suggests to select two categories only, to focus on two. One, slag fly ash-based geopolymer cement. Fly ashes are available in the major emerging countries. Second, rock-based geopolymer cement. Geological material rich in iron is present in all countries throughout the world. The Wagner's geopolymer concrete belongs to the first one, slag fly ash-based geopolymer cement. So it is a slag fly ash-based geopolymer cement officially. I say yes, it is a geopolymer. It is not an alkali activated concrete. The technical data and the problem of standards has been published by an expert who is James Aldred, Technical Director of RACOM. RACOM is a multinational engineering service, worldwide known, very serious, and they helped Wagner's to develop it and to find. This has been published in several proceedings, and it's, I am presenting some excerpts. Geopolymer concrete has been extensively studied by various universities and is starting to gain acceptance in a range of different applications. There are many publications discussing different properties of geopolymer synthesized from different raw materials and activators. Product information sheets and even technical papers may present positive data obtained from different binder chemistries, giving the misleading impression that a specific proprietary material has been comprehensively tested when it has not. Alternatively, papers may also focus on a particular material with very poor performance to negatively characterize geopolymer, and this is practically always the case with alkali activated products. They have always drawbacks. All the leaches are there. Everything is bad. One common concern raised by designers regarding the use of geopolymer concrete is the compliance with the relevant Australian standards. They are speaking for Australia. Standards necessarily develop from the established construction materials and practices which can inhibit the use of innovative materials and procedures. Generally, national standards and codes, which are more prescriptive in nature and explicitly limit concrete to a Portland cement-based binder, are an impediment to non-Portland-based binders being accepted in the industry. What means impediment? A hindrance or obstruction in doing something. European concrete standard, for example, EN 206, includes an equivalent performance concept, but there is a restriction that potential binders should comply with European cement standard and therefore would technically exclude geopolymers which do not contain Portland cement clinker. By chance, they found a loop. They found something totally unexpected. The Australian standard for concrete structure, AS 3600, does not specify Portland cement-based concrete. The components of the standard are only primarily performance-based. So, using this concrete standard, you may use anything provided it provides what is required. And we find now, in the US, a recent ASTM C1157 that is also performance specification for hydraulic cement. The first version of this ASTM standard appeared in 2000, but now it has been better written, represents an important development in this area. So the standards are changing, and this is why we see now applications. ASTM simply requires that the cement meet physical performance test requirements, does not require Portland cement like other European codes. European codes states this Portland so and so. The use of ASTM C1157 is being implemented on small number of projects to evaluate its effectiveness. The Colorado Department of Transportation has been a leader in the use of performance specified cements and has used them on a number of highway projects. So we have, the system is evolving. And because we had entrepreneurs that had dared to do their job by looking at what is feasible, they have opened the gate. And these are the pioneers. And this is what we are looking for, entrepreneurship. We have sufficient knowledge, we have sufficient research that has been done. Now we must apply them, and if it is not in Europe, I don't care. We have sufficient concrete here in Europe, we must apply them where it is needed, and where it is needed, they will change and they will have their standards that do not require Portland. So we must establish the standards for the global economy, and I am proposing my two universal and user-friendly geopolymer system, remember, user-friendly. First, the fly ash-based geopolymer cement, like Wagner's in Australia, and the second, a rock-based geopolymer cement. And of course, we need the industrial hardener that is also used, since it is not just the filler, the geological materials, the powders, aluminosilicates. We need our silicates, soluble silicates that has to be also industrially produced for this application. The rock-based geopolymer cement is iron-rich, and it provides a very important dedication to new type of architecture, and the raw material is found everywhere in the world. Usually I am presenting geopolymer and archaeology, but today I will not. You find sufficient information in my books, and this is the end of my presentation for today. Thank you.